these 2 hours of class, I don't think you can hear it because I tried listening to my own recordings, but like even just 10 minutes into the first class, the tablet that I'm writing on, it makes a lot of noise because, well, it's pushing video uh, and processing audio from this separate USB microphone, and I also have the same computer set up to record. So it's doing a lot for a Surface Pro 3, purchased uh, back in 2013, I want to say, or something like that. So yeah, so right after this class ends and I start one process to take at least one section's video and process the video, which takes another 10-15 minutes or something. I upload that, and then that's usually around 10 a.m. And then the computer on the server side needs to process that for about a half hour, I've noticed, before it becomes available to watch. But then I have an 11 a.m. class, so then I turn off the computer and I turn it back on. It's like normally that hour between my classes, I usually grade things or catch up on emails, but that's not happening. Oh wait, no, don't sit like that. We'll have that same problem from. Okay, I gotta finish this water. Oh my goodness. What am I doing? It is April 2nd, right? Yeah, it's April 2nd. 70, 70, 65. Part of this is also my volume test to just keep talking, make sure that you can hear. Um, I need to do something other than just talking like this all the time because it's already hard enough. I gotta say in class, it's early enough in the morning, and I like say something, and people are like, "Did he really just say that?" But now it's like I don't get the sort of half eye roll or the like, okay, that was funny, but I don't want to admit it or what. There's like at least some interaction normally. So this is more strange, and I'm like, maybe I should go find that other ukulele somewhere or learn how to play banjo or something. Um, yeah, something to. Oh, geez, 15 seconds. I gotta finish this thing. Oops. All right. Let's just put that there. Okay. All right. Welcome back. It is Thursday, April 2nd. Um, just a round of announcements here. I mentioned yesterday, if you've got any questions about logistics, please ask them. Or now, if you have something that I can address, you can unmute your mic and just ask. Make sure that kind of how things are going are clear, or just send me an email. That said, I think sometimes people have interpreted that as an interpretation to ask math questions by email. I've tried in the past. I mean, before all of this insanity, I mean, just years ago, people would ask things by email. I'm stuck on this Weber question, and they would either screenshot or maybe even try to send like by a picture, an email. They might send their work, and it's like sometimes there's enough problems that like I can't. I want to ask a next question after the first question, or what happens is people kind of get stuck multiple times in the same question, and like. So I've tried doing this. Like, okay, I'm gonna need to explain it this way, and then before I hit send, I'm like, wait, that's probably not clear, and so then I write something longer, and it takes 30 minutes. It takes 45 minutes, and I've gotten just a one sentence reply back of like, I didn't understand what you wrote. I'm like, oh, well, yeah, I guess not, because it's just hard to do these things over email. So if you've got a question, I think about math, the thing to do is to really join office hours. Um, I know it's even a little more difficult, but I've had some people joining. I've had, in fact, I shouldn't name any names. I won't do that, but I've had somebody come quite often, and I will say I think that the student has found it very helpful, and I write on screen kind of like this, and it's easy to, I think, to be really honest, in these questions to get stuck. Not that I tried designing them that way. It's just when you take a derivative, and then often when you take a second derivative, you set equal to zero. You know, the equation that you have to solve, it's a lot of algebra. There's a lot of factoring. I cannot emphasize just how much factoring there is. And one of the processes I've been going through, especially with like that one somebody who's, you know, been visiting quite a bit, is just this like factor and all, and then you know, they'll do a step or two and then ask, well, then now what? And then I'll say, keep factoring. Look at this part of the problem, and then, you know, I'll underline it on screen, and then I'll say, okay, did you factor? And then I'll ask, can you repeat that? And I'll write it the way that I heard it, and then, you know, then I've heard like, yeah, that's what I did. And I'm like, okay, but there's actually an error in the step, right? So it's like, it's hard to have these interactions. I mean, I know it's more challenging even in this format, but what I'm saying is email itself is not really creating an environment where when you're stuck in the moment, I can ask something to help you get unstuck. Or if you're just say, I have no clue, I can just give the next step. But like, there's not much I can do in interacting and find out your thought process and so on from an email. That said, I know that there are complications related to this process. So, for office hours, use this video conferencing thing, sign in the same way. If for some reason, because I know we haven't really had an opportunity for you all to test your sharing of audio with me, but if for some reason there's some technical difficulty there, you can't just call my office phone number. Now, clearly I'm not in my office right now, but I had sort of anticipated we were going to have some kind of situation where we would not be, or where even I would not be allowed on campus, which is actually the case. Basically, one of the last times I left my office back in like March 10th or something like that. Yeah, I think 2 days before our exam, I just set up my office phone number to forward to my cell phone. So if you call the office phone number, I will get it actually. And so if necessary, during office hour times, you can call the number. So long as it's not busy, meaning somebody else hasn't also called in. And that's at least an option for audio. So even if like you can watch the video screen as I write on screen like this, but if we seem to have any audio connection problems, at least that's an option for audio. Additionally, so you can, if my office hour times don't work, please send me an email. Just like in the past, I'd be more than happy to set up an office hour by appointment. I just can't answer the math question back and forth over email. Like I'm behind as it is with grading and so on. In addition to my office hours or setting up an appointment to meet online, I just want to mention the Murphy Learning Center is still up and running. So almost all their hours are represented. So you can just drop in tutoring there as well. And then I should comment that the date scheduled for exam 3 is next Thursday. The way things have been going this week, it's I've been like finishing slides for our morning class, like every day. It's been the night before at 10 p.m. It's just like that's how many other meetings and things have been going on. So I am not as organized as I'd like to be related to exam 3. Now here's an easy enough thing for me to do is post some practice materials like in the past. Like I have, as I did for exam 2 and exam 1, I didn't write new practice exams. I've taught this class so many times, like the old practice exams are still applicable. So I can easily do that. I can take some old material, and just so that you have the math to practice, I'm going to post the practice stuff as soon as I can, hopefully by noon, maybe by 1 p.m., something like that. I'll get those things posted just so that you have the practice material. For the format, I have some ideas brewing in my mind for what to do, but I'm not sure yet. So I need to test a couple things. So I don't want to like say, oh, we'll do this and then have it change. So I don't want it, especially in a recording, right? Or somebody listens to this and doesn't listen to the other thing. So I'll just say I'm working on it. I've got some ideas. Once I've tested a couple things over the weekend and figured it out, I'll send an email announcing a bit more of the format of exam 3, and I'll also do what I can to get a practice exam that's in that format as well, so you can test the format in Canvas. So Anyway, I know that's a lot of tentativeness, but if for now, maybe worry a little less about the format and think more about the actual math material of it. I'll get that practice stuff posted today. Finally, I forgot to put this in the slide, but today is a Thursday, so there's a quiz today. So please complete that online quiz at some point during the course of the day today. Those are my announcements, but I will pause to see if anybody's got a question about any of the logistics. Okay, my original plan for this particular class day, so for the every time I've taught 175 in the spring, the Thursday after spring break, I have used as we did a day of curve sketching in class, and now it's a chance for you to practice. I think format-wise, I would have really liked that, and I have some practice questions for you to try sometime after class, I guess. But like, I think maybe for now, the better format, perhaps, I'm not sure, is to just run through some of a couple of these. So I'd like to try the curve sketching method that was introduced yesterday on this function f of x equals x cubed minus x squared minus x. First of all, there's information you can get without taking a derivative at all. So before even computing f prime, notice the domain is all reals, right? Because there's no dividing by zero. There's no worry here about square rooting a negative. There's no... also, for logarithms, you want to make sure that the input to your logarithm is positive. None of those things appear in this function the way it's written. So since the domain's all reals, the other thing is there's no x values that are just right outside the domain. Like, like yesterday, I think it was with x equals 3, that was like we wrote in interval notation and 3 wasn't included. There was a parenthesis, so like there's no x value just on the edge, just on the cliff. And that's where you'd normally look for a vertical asymptote. So this is already telling us, since there's no x values on the edge or just outside the domain, there's going to be no vertical asymptotes in this one. So I'm already jumping around a little. I'm not doing all the steps as presented yesterday in precisely that order. It's not step 1a followed by step 1b. I think this was like step 1a followed by 1d or whatever, right? Y-intercept, you can have up to one y-intercept. You cannot have more than one. To get the y-intercept, you got to plug in x equals 0. So I did that. Back to the original function, 0 cubed minus 0 squared minus 0. You get 0 as a y-intercept, in other words, the origin. What about x-intercepts? Now for x-intercepts, we should set y equal to 0. Y, by the way, is this thingy here, right? So where the f of x is, we can pretend that that's a y instead. And if you replace that y that I just drew with a 0, you'd have this equation here. Now you might stare at this equation and go, oh, I gotta solve that. Well, it is a cubic. And that's what makes it maybe more painful, right? If it's a quadratic, we've at least got the quadratic formula. But this is a cubic. What are we going to do? Well, notice that all three terms have a factor of x. So let's factor out an x, right? Name of the game is factor. So I factored out an x here, and I also swapped the two sides of the equation. So I wrote, you don't have to, but I just, now the 0, which used to be on the left side over here, I'll circle it, is now on the right side. But yeah, if you factor out an x, then in parentheses, that's the other thing I want to re-emphasize, because I keep running into this. It's a place people are getting stuck in office hours, but I want to remind you, when you factor, you always create a new set of parentheses. So you factor out an x, and notice there were no parentheses over here in that text I underlined, but there's a new set of parentheses right here. So inside the new set of parentheses, it's what's left, and you have an x squared minus x minus 1 is left. Okay, so then we factored in part, and now we have a quadratic inside the parentheses. So we should say, oh, that's easier to deal with. A quadratic is easier than a cubic to deal with, and we should try to factor that. Now, if you try, you might scratch your head and go, I can't seem to factor that. And yeah, it is problematic to factor. First of all, when you there's two thingies, right? There's the x factor, and then there's the x squared minus x minus 1 other factor. And you set each of those equal to 0. When you get set x equal to 0 and you solve that equation, there's no action you have to take to solve that equation, because x is already isolated. So x equals 0 is an x-intercept. When you set x squared minus x minus 1 equal to 0, and you try to factor the left side, it doesn't work out so well. But it is a quadratic, so you can apply the quadratic formula. And that's, I on this slide, I'm not doing every little detail. I'm trying to give you a big overview. So I'm sparing you the detail. If you need to go look up the quadratic formula, please do that. You'll get here x equals 1 plus or minus root 5 over 2. These are what I would call messy numbers. They're not too bad, but what I mean by messy is it's not like it'll be something 0.75. Right? That's not how it ends after the decimal. Right? This root 5 is just a rather messy number, but hey, at least it's a real number. This is not complex. If you take a look from the quadratic formula, there's a chance you can get complex numbers, right? Because of that square root, you might be square rooting a negative, but that doesn't happen here. So you get actually, in addition to the x equals 0 that we had, you get these two more x values, once using the plus sign and once using the minus sign. So there's a total of 3 x values that are x-intercepts. That makes sense when you solved an equation up here that was a degree 3 to get 3 solutions. I want to comment about these two real numbers. One of the numbers is positive, and then if you stick the minus sign for the plus or minus sign, then the fraction is going to be negative. First of all, the number that's positive, real easy to argue that's positive because there's no minus signs anywhere. The next number takes a little more work to explain, though, so I would like to argue, why is this fraction here, why is that a negative number? And my argument, I hope I can convince you this just by saying root 5 is bigger than root 4. Yeah, root 5 is bigger than root 4. Or I wrote this here, root 5 is bigger than, I just simplified root 4 to a 2 though. Okay, so if root 5 is bigger than root 4, or root 5 is bigger than a 2, then take a look at this fraction's numerator. You've got 1 minus root 5. Now, look, if you had just 1 minus 2 in the numerator, you'd already have a negative numerator. But you've got 1 minus a number that's even bigger than 2. So when you do 1 minus an even bigger number, that's, if you had a negative before, then you definitely have a negative still. So the whole point at this point is to say, yeah, we've got this fraction and we've got that fraction. And in a decimal format, it's kind of hard to tell what numbers that we have. But at least we know that we've got an x-intercept that's 0, we have an x-intercept that's positive, and we have an x-intercept that's negative. And beyond that, like what specific number, we don't need really much more detail than that right now. Okay, I didn't, for this one, bother with trying to look at horizontal asymptotes. And part of, I think, the thing that you'll notice with these is you've got to develop a bit of your own style. You've got to like look at that kind of longer list of tasks involved in graphing a function and think about which things are most appropriate for which function, and it takes a little bit of style developing, some personal taste. So I wanted to move on to what do you get out of f prime. So looking back to f written at the very top, first line, let's compute a derivative one term at a time. Yeah, 3 separate terms, 3 separate derivatives using the power rule, 3x squared, then after the minus sign a 2x, and after that minus 1. Now, not only did I compute the derivative here, we're going to build a sign chart in a moment for f prime, and we should ask the 2 usual questions, right? The only x values you should label on your sign chart for f prime are where does f prime not exist and where is f prime equal to 0? For where does f prime not exist, again, this underlined thingy here, this always exists. There's no dividing by 0 kind of issues. There's no square rooting a negative danger or anything like that. So f prime always exists. Where's f prime equal to 0? That's where the factored version of f prime is more helpful. Now I know it's a little more painful to factor this, but at least you have a quadratic. You know, this degree 2. At least it's not a degree 4 or something like this. And to factor, it is a little more challenging because of the 3 that's in front of the x squared. But at least 3 is a prime. So 3 is like, you know, it's going to be either a 1 times 3 or a 3 times 1. So that feature you see with the number in front of x is a 3, and the hidden number in front of this x is a 1. Is a 1. The hidden number is a 1. Yeah, it's a little more work. It's a little more challenging when there's a number in front of x squared that's not 1, like this 3 that we have here. But you should give it a try, or quadratic formula, I guess, right? But like, the thing is, this would be much more work had the number in front of x squared been very composite number, like 24 would be like 1 times 24 or 2 times 12 or 3 times 8. It goes on. There'd be a lot of options, but here it's like do a little bit of guess and check to find the factoring. So based on how this is factored, it's a lot easier now to answer the question, where does f prime not exist? Or what x values makes f prime not exist? So when you set this thingy equal to 0, then you get to set each individual factor equal to 0. Setting 3x plus 1 equal to 0 will eventually give you x equals negative 1/3, and setting x minus 1 equals 0 gives you x equals 1. So here I am, excuse me, not doing all of the algebra steps, at least showing them visually on the slide. I think, also, you'll notice I'm not doing this thing where, okay, we developed the part of the f prime sign chart and then we picked the x values, and I didn't show all of that work. I'm just right now leaving it to you to work on some of those details. You've seen this now kind of every day this week, and also saw it the 2 days before the exam, the week before spring break. So you've seen so much of that. I hope now that you're like, okay, you can piece together where did the plus and the minus and the plus come from. I had to pick some x values clearly, right? I probably picked x as 2. I probably picked x as 0 to get this minus sign, and I probably just picked x as negative 1 and I plugged into the factored version. For me, that's easier. If you prefer to plug into the other version of f prime, your call. You should still get a positive. If you plug in x as negative 1, this underlined thing here should still become positive. You can check. But then this information about f prime being positive, negative, positive tells you something about f. It tells you where f is increasing, decreasing, and increasing. Now the other thing I want to do is let's think about if f is increasing and then f is decreasing, what's the graph got to look like? So I don't even want to draw axes right now. I want to like it's going to be a very relatively inaccurate picture, but the thing about the picture I want to think about is if you've got increasing, that's like that, right? So you're going up the hill, not like this. So I just erased, but this, here's a picture of decreasing. Okay, so going down the hill. So if you got increasing, followed by decreasing, and in fact, for a moment, you've got f prime is equal to 0, meaning, so sorry if this is too pointy right there, I'm going to try again. But if f prime is 0, please remember that f prime, that the derivative is slope of tangent line. So you've got increasing first, then you've got a moment where the slope of the tangent line is 0. That's what derivative means, slope of tangent line. And then you have decreasing. Right, so there's this moment at the top. Maybe I'll just try to highlight that point. A moment at the top where if you were to draw on a tangent line, the slope would be 0. That's what derivative is 0 means. So increasing, slope 0, that followed by slope 0, followed by decreasing. That tells you right there you're at the summit of a peak. Right. This is the top, the very top of a mountain. So you've got a local maximum, don't you? Right. If you were to graph f, you're gonna notice a local maximum. And then I want you to think about, please, and maybe I'm going to get a brave soul to answer this by unmuting a microphone, but if you have decreasing and then increasing, draw a little rough sketch. It doesn't even have to be on axes because we're not ready for that yet. Just what's going to happen? What? Anybody want to unmute a mic and just share a couple quick words? We got decreasing, and then at 1, the slope is 0, and then we got increasing. Okay, I got a typer. All right, so thanks TJ. All right, so I got okay, local min. I agree that's what you'd have here, and I won't make anybody maybe type or speak a reason, but let's just I hope the sort of little mini drawing you had was okay. F is decreasing, followed by a moment just a brief moment when x equals 1 where the slope is 0, followed by f is increasing. And so that should create the bottom part of a valley right there. And so here you'll have a local minimum. Okay, so I hope we're okay with this. I mean, this is there's a lot of this information about where there's a local max and local min. It's officially, technically, what the first derivative test is trying to talk about. But I don't personally prefer trying to memorize that thing word for word. I think it's much easier to just keep working back at like, oh yeah, f prime positive, well, positive slopes for your tangent lines have to correspond to f is increasing, and then tend to imagine that of like climbing up a mountain and then going down a mountain. So that means you reach the top. Yeah, so I have it here at the bottom as well, that f has a local max, f has a local min. Now, here's the thing. Top of next slide, I want to organize a little different collection of info. So I put the function there for reference. Here's f prime, and we had two ways of writing f prime. Let's now look at concavity of f, meaning we need f double prime. And if we're going to look at f prime and take another derivative, which of these two f primes would you prefer to look at to take a derivative? See, my preference is to use this version of f prime that I just underlined. Like that. You could use the other one. The other one is factored. But if you differentiate that one with the two sets of parentheses, you have to use the product rule. And that's fine. You'll get the same final answer that I would. It's just, I think if I can avoid using the product rule, I guess I'll do it, right? And so differentiate 3x squared minus 2x minus 1, one term at a time. And you get a 6x minus 2. Name of the game is factor. So you factor out and you have 2 times quantity 3x minus 1. When you set 2 times quantity 3x minus 1, that's one way of writing f double prime. You set that equal to 0. You get to split this up as 2 equals 0, no solution. 3x minus 1 equals 0 has a solution, and that's the x value 1/3 that's written there. That's the only x value to write on the f double prime sign chart. I picked an x value that's bigger than 1/3 and plugged into this version of f double prime and got a plus for the value. I picked a number that's smaller than 1/3. You could pick like 0.1 if you wanted to, but you could, just pick 0, I guess. And then if you, plug in to there, plug in 0 for x, you ought to get that f double prime is going to be negative. Yeah, 2 times 0 minus 1. Yeah, or 2 times negative 1. Sure, yeah. So this information in the f double prime sign chart tells us something about f, right? So f double prime being a negative says that f is concave down. F double prime being positive says that f is going to be concave up. So there's a change of going from concave down to a concave up situation. So right there at that x value, right where that transition occurs, where we already said it was x is equal to 1/3. Right there's going to be an inflection. However, I want to remind you that an inflection point is a point. I mean, like a point meaning having an x coordinate and a y coordinate. So what's the y coordinate of the point? Often what people try to do is they will compute f double prime of 1/3. I would not do this. Okay, so this is an error that people will make to get the y coordinate of the point. They'll plug in to get this y coordinate where I've just squiggled right there. They'll plug in 1/3 into f double prime. I'll tell you right now what number you'll get if you plug in 1/3 for x. You ought to get 0. I mean, that's what this information is right here. Right? So I've got it on the next slide. You already know that f double prime of 1/3 is equal to 0. That's what this says. So I've more than ever in previous semesters, I've tried to emphasize that these are x values down here. So when you plug in x's 1/3, the value of f prime is that 0. So, I mean, you can just check if you want by plugging in. to either version of f double prime that I boxed. But I tried to emphasize that the things written above the number line, so like that's the value of, in this case, f double prime. So the value of f double prime is 0. The value of f double prime is some number that's positive. That's all we cared about. Here, this minus sign, the value. So I'm trying to, x coordinates below and the value of the function above. But that's f double prime. And the thing is, an inflection point is supposed to be a point on the original graph. So here's the part where you've got to be real careful that we've got three functions, f double prime, f single prime, and f. You need to plug into f. So here it is. I took this x value of 1/3. So here, maybe I'll say it this way. The second derivative is what you set equal to 0 so that you discovered at which x value you had an inflection point. And because of that, it's too easy to be distracted and want to plug in the x value that you get into f double prime. But if you do, you should always end up getting the y coordinate to 0. But that's not what's going on, right? You can't assume that that's where the inflection point is located. To get the point on the graph, you've got to go back to the f. So you plug in. There's a bit of algebra here that I left out. When you do 1/3 quantity cubed, you got to do it's 1/3 times 1/3 times 1/3. You have a 1/3 times 1/3 for your 1/3 squared. You got to do your multiplications before your subtractions because of order of operations. You're going to have fractions with different denominators. So common denominator, all this mess, not worth sharing all visually right here. You'll get the number negative 11/27, meaning that that's the y coordinate. So for your inflection point, yes, x is 1/3, but the y coordinate is found by plugging into f. And so this negative 11/27 from the previous line, that's the y coordinate of the inflection point. As long as we got the x and y coordinates for the inflection point, and I think it's actually a good thing at this point to mention, why not also get a couple other points? So a slide ago, we had said that there was a local max when x equals negative 1/3, not positive 1/3, but negative 1/3. So look, if there's going to be a local max, right? So that's like the top of the hill, somewhere in the picture, we might as well get the coordinates of that point as well. So we already knew from the previous slide that the x coordinate would be negative 1/3, but what about the y coordinate? Well, again, go back and plug into the original function f. It's too tempting when talking about local maxes to plug, since you had just dealt with f prime, it's too tempting to just plug in this x value of negative 1/3 into f prime. But you need to go back to the original function to talk about a point that's on the graph of the original function. So I showed even less work than right there, but if you plug in negative 1/3 all the way up here into the f that's at the top, you end up with 5/27. So the peak the peak that we'll draw on the graph has x coordinate negative 1/3 and y coordinate 5/27. And same deal, you can do this with the local min. Earlier we said there's going to be a local min at x equals 1. And 1 is a lot easier to plug in. I can even talk through that one when you plug in x equals 1. 1 cubed minus 1 squared minus 1. Yeah, so 1 minus 1 minus 1. That should be a negative 1. So there's going to be a point in our picture that's a local min. So wherever that valley is, there's going to be a point here where the coordinates of the point are a 1 and a negative 1. Okay, that is a lot of data between the last two slides. And even not showing all of the work in every full bit of detail, that took up 2 slides. What I have at the top of the next slide is the vast majority of facts that we have just gathered without any of the work to show for it. So we talked through the work. What I want to do is have as many of the facts visible here so that now we can talk about the graph. So the first item talks about the intercepts. The second one tells you where f is increasing or decreasing. The third item tells you about points. Here's the thing. For some strange reason, I don't know why they did this hundreds of years ago, but the notation for points and the notation for intervals looks really similar because they all pretty much look very parentheses happy. And so the things that are points, I labeled in blue. So the blue ones are not intervals. The blue ones are x coordinate, comma, y coordinate. I don't. It is what it is. So, yeah, the third bullet here mentions the local min point and the local max point that we just computed at the end of the last slide, and then we've got intervals of concave up and concave down for the fourth bullet, and then the fifth and final bullet here tells you that inflection point. So this is a lot of data that we had just computed. I plotted, or rather had the computer plot these 3 points. I should talk through this a little bit because it looks a little confusing. It's tempting to just want to draw a straight line between these 3 points, but that can't be right. I mean, the function has increasing parts and decreasing parts, and this straight line that I drew is just all decreasing. There's no concaveness shown in this, so that can't be it. So let me try to talk through the points. There are 3 points that are shown in blue. Sorry if the blue is not showing up very well on your screen. If you download the slides, I think you'll see that blue rather clearly. But the x coordinates of the points we have here are 1 and negative 1/3 and positive 1/3. So the point furthest to the right, that's that one. So that's the local min point. So spoiler alert, eventually the graph local min point, it's going to look like that. The local max point is when the x-coordinate was negative 1/3. So spoiler alert, at some point the graph is going to look something like that, right? And then the inflection, it's harder to draw what an inflection looks like because on one side you have concave up and on the other side you have concave down. But just so that you have a little bit of a reference for which point is going to serve which role here. And even in the process of graphing, you've got to develop a method that works for you. So I'm going to explain it one way, and you've got to decide, I like that or I don't, and develop your own thing. That's fine. What I'm going to do is I'm going to ask what happens in this part of the graph until we get up, just right up to that first point here. So this point where the x-coordinate is negative 1/3. Well, let's see. It looks like this interval here applies, right? So f should be increasing. And so if I were to draw f is increasing, this is my first picture. I'm going to erase it because it's not accurate enough. But at least I'm showing that f is increasing. The thing that's not shown here is the concavity. It's not this one that applies. Concave up happens once you look at x values past 1/3. We've got this interval is currently applying. In fact, concave down applies until you get to this. Okay, I know it looks confusing again, but this is an interval, so that's not a y value here. This happens until you get to the x value of 1/3 right there. So we should have concave down, right? We've got concave down and increasing. So this picture doesn't really, it shows increasing, but it doesn't show concave down. So let me fix that and say that the picture looks, oh geez, come on, pen. Looks something a little bit more like that. Okay, that's increasing and concave down. Now what happens? Here's where you kind of just got to stare at the stuff you have and go, okay, are we still increasing? Are we changing to decreasing? Let's see. Oh yeah, we were increasing up until this x value of negative 1/3. Now that we're looking at x values beyond 1/3, so this was the 1/3. This was 1, by the way. Right. So for the next little bit, we're gonna have decreasing applying. Right. So, what about the concavity? Let's see. Oh yeah, we'll stay concave down until we get to x equals 1/3. So that would be this point. So we got concave down and decreasing applying. So you get a thing that looks like this. I should comment, we did earlier say that the y-intercept is 0. So my picture is not doing a good job of that. Let me fix this. Y-intercept being 0, meaning you go right through the origin. So, something like that. I tried to get a little, it's hard because the points are close-ish to each other, but I tried to depict a bit of this concave down nature in addition to the decreasing thing going on. Now what happens? Here's where the concavity changes, right? Because we're at x equals positive 1/3. We said that when x, that's the inflection point. So what's changing here is the concavity. We had concave down before. What we're going to draw now is concave up. We're still in this decreasing mode because we keep decreasing until the x coordinate is 1. So the thing changing is concavity, although we're still decreasing. So that's a picture of concave up while decreasing. And then what changes when you get to 1? Oh, that's where decreasing no longer applies. Now it's this interval, right? X values between 1 and infinity, that's when f is increasing. So we're still in this concave up mode, but f is increasing. So concave up and increasing would look something like that. So you'll notice that in the work done here, I focused mainly on the intervals of f increasing, decreasing, and the intervals of f concave up and down. So we should check the rest of this stuff. If it was, yeah, I guess we did work on the x and y intercept at the origin, but then there were these two other x-intercepts. Remember, one was supposed to be positive, one's supposed to be negative. Yeah, we've got that. Here's a positive x-intercept. There's a negative x-intercept. Are those exactly where the points are? I don't know. It's close enough. I mean, this is all that you should be expected to do without a calculator. So, at least you've got a positive and a negative x-intercept as well as 0, the origin here being an x-intercept. Local max point. So when x equals negative a third, right there, is that really truly a local max? Yeah, it looks like a hill, like the top of a hill. And then local min point, right over here. Right there. Yeah, that looks like a local min point, right? It's the bottom of a valley. And then an inflection point right there. If you look at that point, to the left of that, the picture should be concave down, and to the right of that, the picture is concave up. Okay, so this is an involved process, as you'll notice. There's an accurate picture from the computer, close enough. For the next function, just to talk through some of the examples of same general idea, I'd like to start with the function x times e to the 2x. Ooh, sounds like a product rule is going to happen. And here, you've already just been given information. You don't have to compute it. Sometimes some of the functions don't fit our techniques very well, so sometimes just information is given to you. So we're given information about some limits and just told to graph. Here, the domain's all reals. The function we have up here, there's no logarithms or dividing by anything. So yeah, the domain's all reals. There's going to be no horizontal asymptotes because of that. To find a y-intercept, please remember you got to plug in 0 for x. So when you do that, you've got a 0 times, e to the 0th. Anything to the 0th is a 1. So you have a 0 times 1, which simplifies to a 0. Okay, so you get that y-intercept of 0. X-intercepts, plug in 0 for y. So this f of x up there, I'm pretending that that's a y. I replace that with a 0. And so I have 0 is equal to x times e to the 2x. Take a look. This is a product. So whenever you have things multiplied together equaling 0, you can always set each of the individual pieces equal to 0. So I set x equal to 0. I set the other piece, e to the 2x, equal to 0. The first part, x equals 0, solving that, not so bad because it's already done, right? So you got to isolate x. It's already been done for us. For the next one, e to the 2x equals 0. That actually has no solution. The reason is, e to the anything is, I'll remind you from like 2 days ago, I think, e to the anything is always positive. So e to the 2x, no matter what you plug in for x, e to the 2x is always bigger than 0, so can never equal 0. This has no solution. This means that the only x-intercept is x equals 0. Now, if you take a look, the only y-intercept is y equals 0. The only x-intercept is x equals 0. This actually tells us that the only intercept of any kind is the origin. Meaning, if we were to graph this function, the only time the graph should touch either the x-axis or the y-axis is directly at the origin, right in the middle of the picture, nowhere else. So if, it's kind of good information to have as a quick check at the end. So if after we draw, if the picture goes through other places besides the origin, we go, oh wait, something seems wrong about that, right? So it's just information to have. I wanted to get information from the first derivative to practice some of the calculus of what we have. But take a look. Our function here is a product, so we've got to use the product rule. So we've got the first x times the derivative of the second. So when you differentiate the e to the 2x part up here, that requires the chain rule. So we're combining product and chain rule. The derivative of e to the 2x is e to the 2x times the derivative of the inside part. That inside part being 2x, its derivative is a 2. The second half of the product rule is this. So you've got the second part, e to the 2x, times the derivative of x. The derivative of x, I remind you, is 1. Okay, so yeah, this is a good reminder of our derivative rules as well in this process. And let's see. So just to slightly clean up how the function is written, before the plus sign are things multiplied together, the x times e to the 2x times 2, and you can put those in any order you want. Look, the name of the game for these things is to factor. So notice that e to the 2x is part of both terms, so you can factor that out. Whenever you factor, you can always draw a new set of parentheses. So you've got e to the x, e to the 2x outside the parentheses, and what's left inside the parentheses in the new parentheses is a 2x plus 1. So in drawing a sign chart for f prime, what x values do we label? Always ask the same two questions: is where is f prime undefined? And well, that doesn't happen because there's no dividing, there's no logarithms, there's no square roots to worry about. And then where's f prime equal to 0? So when you set this thingy equal to 0, you get to set, because it's a product, you get to set each factor equal to 0. Right? So when you set e to the 2x equal to 0, e to the 2x equals 0, that part has no solution again. When you set, for the same reason we just argued it up here, right? E raised to any power is always a positive number, so you don't, it doesn't matter what you plug in for x, you can't get e to the 2x to equal 0. 2x plus 1 set equal to 0, and you'll get, as an only solution, you'll get x equals -1/2. So that's the only x value to put on the f prime sign chart. I picked some test values. Maybe I won't talk through that. You can check the details of, you'll get an f prime as a minus, and then with a different x value, you get f prime as a plus. Of course, we could talk about how this minus tells you that f prime is, so this minus for f prime tells you that f is decreasing, and then this plus for f prime tells you that the original f is increasing. So think about that. So you've got decreasing and then increasing. That should create, as we said, as I asked you all about earlier, that should create a local minimum. So there's a local minimum when x equals -1/2, and we should, earlier you saw because I kind of ran out of room on slides. We organized getting points later, but there's space here for this, so let's plug in x is -1/2, not into f prime. If you do, we know that we're going to get the value of f prime is going to be the 0. Let's plug back into the original f up here. So if you do so, there's the work, but the point is that you're going to get f, original function f, so no prime here. F of -1/2 ends up being -1/2e. You can look at some of the algebra steps there. The point being that x coordinate -1/2, y coordinate -1/2e, that's going to be a local minimum point. So that point, if we graph it to help anchor the picture, ends up being a valley. So somewhere in the picture you've got this kind of shape going on, and here would be the x and y coordinates of that point. You might look at that and go, wait, -1/2e, what are we supposed to do with that? And even here, I'd say without a calculator, you can do things. So just, you got to remember, I think people freak out about e maybe a little too much, but the thing to please remember is that e is approximately 2.7, or we can just pretend for now that e is 3. So -1/2 times 3, okay, so -1/6. -1/6. That'll work. That's close enough for us for what we're going to do. Okay. So here's the original function. Again, on top of next slide. We had f prime, and I'm showing you the two different ways that we've written f prime. And uh, I guess the question I want to ask is, which version of f prime do you want to take the derivative of to look at f double prime? In this version, you'd have to use the product rule. So it's not the version I'd prefer. I would like to differentiate this one instead. Actually, it looks like we're going to have to use the product rule anyway, right? So what I did was, let's not look at that one. Over here, just to organize the work, because there's 3 pieces, I drew some parentheses so I only deal with 2 pieces there. But that's still a product. That's all I did, going from here to here. We have to use the product rule anyway, but like using the product rule directly on this one looks a little like more work to me. Again, it's up to you. You got to you'll get the same final answer. But all I did then was I organized some parentheses, and I'm going to apply the product rule to this so that with the parentheses, I hope it's a little clearer what's my first and what's my second. So here's the derivative. The first 2x is copied. The derivative of e to the 2x requires a chain rule. That should explain the other 2 in what I've underlined. The other half of the product rule is to copy the second. So copy e to the 2x, and then differentiate 2x in parentheses. That derivative is the 2 in parentheses. And then finally, don't forget, after copying this plus sign that I just circled, we need to differentiate there's still this one other term that it wasn't a participant in the product rule, but there's this e to the 2x, and the derivative of that is e to the 2x times 2, that times 2 coming again from the chain rule. Okay, so there's f double prime. And we ask the same 2 questions we always do in building a sign chart. So where does f double prime exist? Or, so, excuse me, not exist? Well, f double prime exists everywhere because there's no dividing by 0 kind of issues. But then where does f double prime equal 0? Here's where it helps to factor. And you might say, well, what am I supposed to factor out? And just factor out whatever you notice. Because and even if you factor differently than somebody else, it should still work out. So I had this great question come up in office hours recently of like, well, what if I factor things in the wrong order? And that's not really a thing. Like you can factor in a different manner than somebody else. And if you just keep factoring, you'll get to where you need to. And as you factor, you'll discover more things that factor out. So for instance, I noticed e to the 2x, and all I factored out is an e to the 2x. It was late last night. Maybe you noticed, wait, why did you just factor out e to the 2x? You could have factored out e to the 2x and also factored out a 2. But whatever, all I saw at the moment was factoring out e to the 2x, and left inside parentheses was a 4x plus 2 plus 2. And even here, now I notice much clearer that I could see what's in parentheses and factor out a 2 out of each term. Or you could just simplify the 2 plus 2 as a 4. That's what I did. Again, there's no, as long as your algebra steps are accurate, you won't get stuck. So just factor or simplify what you see. Now I see I can factor out a 4. So I did that inside my parentheses. I have x plus 1. You can arrive to this stage using so many different possible steps. So you got to just pick something, and when you see after you start factoring and you simplify what's left inside the new set of parentheses and simplify that, then often you'll see more factoring. I mean, some of these factoring problems are rather involved, and that's why if you actually go back to WebWorks 0, not that I'm asking you to do WebWorks 0, I would challenge you to go back and look. There were places where I took a function, I didn't even state what function, I took a second derivative and I set it equal to 0, and that's what I presented to you in WebWorks 0 quite a lot, was just here's this wacky fraction. I set it equal to 0, solve that equation, knowing that we'd be doing this. So look, when you set each of these, so when you set this equal to 0, you set the you get to set each piece individually equal to 0. Setting e to the 2x equals 0, as we've kept saying, it has no solution. 4 equals 0 also has no solution. X plus 1 equals 0. Of course, has a solution, the only solution being x equals -1. Here's a complete f double prime sign chart. This concave down for f and concave up for f tells us that there's going to be an inflection in f at x equals -1, and we can get the inflection point. Again, the issue I want to try to remind you of is don't plug in -1 into f double prime. If you did, you know that you're going to get f double prime of -1 equals 0. That's what this was about. Instead, go back to the original function f, which is why it's up here for reference. This, using some algebra, is going to clean up to become -1 over e squared. So the inflection point has x coordinate -1 and y coordinate -1 over e squared. You might say to this, what am I supposed to do with this e business again? But please remember that e is close enough to 3. So close enough to 3, then this is -1 over 9, right? So I think the other thing maybe I should point out right now, as far as a general helpful skill that transfers to other questions like web work questions and so on, is sometimes you want to deal with f prime this way, sometimes you want to deal with f prime that way. Same deal. Sometimes you want to deal with f double prime in this format, sometimes you want to deal with it as factored as possible. And there's this interplay of going back and forth between the two methods. So let's take, here's a summary of all the info that we've had. I plotted the 2 points, or rather had the computer do this, and you might say, can I have done this without a computer? And I'll argue, yeah, because look, the point where the x coordinate is -1, the point where the x coordinate is -1/2. Take a look. This point here is drawn a little lower, and I hope this makes sense because the y coordinate was approximately, let me just write this in here as I did last section. The y coordinate's approximately -1/6, we said. Over here, the y coordinate was approximately -1/9. And so you see this, I think, in the picture. So yeah, both of these y values are negative, but the 1/9 means it's a tinier number. It should be a point that's closer to the x-axis. So I think you see these features, and you see if I just label that when the x was -1, this is going to be the inflection point. And over here we had a local min point. Local min. So local min, it's going to have this kind of shape to it, generally speaking. You'll notice that the picture should start concave down and decreasing. So you've got this until you get to the inflection. So sorry, you can't really see much of the concavity here because there's just not a lot of room. But that's maybe a little better. You can kind of see the concave down a little better there. And then since there's an inflection, there's going to be change. Now the concave up piece is going to apply, but we're still decreasing until you get to the local min. At the local min point, that's where we're no longer decreasing. Now this interval, we're at the point where you've got increasing beyond x equals -1/2. So something like that. Actually, there's an error that I have here. We had stated quite a while ago that the only intercept should be at the origin. So I should get rid of that and instead say, you know what? If the graph is to go through the origin and be increasing concave up, the picture looks a little actually more like this. What I have, I know my time is real short here, is the graph in Desmos. So I would encourage you to type this in, to do x times e to the 2x in Desmos yourself, so that you can see right here the local min when x equals -1/2. Since I am out of time, I will just remind you all that, here are some practice questions. These are the ones that, had we been meeting in person, I'd have just handed these out on sheets of paper and said, just try these and I'll walk around. That was the original plan. I have the announcements here again that I started class with. I think the key one I want to remind you, because of the timing, is please do the online quiz today. And I'll see you either next Monday or in office hours later today, and please look for an email this weekend about some details about the format of exam 3. All right, thank you.